For a generic redox reaction where the reactants turn into the products, the free energy is related to the potential for the redox reaction. The equation that relates free energy and potential is given by delta G is equal to negative NFE. Delta G is the instantaneous difference in free energy between the reactants and the products. N refers to the number of electrons that are transferred in the redox reaction. F is Faraday's constant, which tells us the charge carried by 1 mole of electrons. So 1 mole of electrons carries 96,485 coulombs. E refers to the potential of the redox reaction. You could also call this the voltage of the redox reaction. If the reactants and products are both in their standard states, we can add the superscript naught to delta G and the superscript naught to E. So we can use this equation to calculate delta G naught from E naught, or vice versa, we could calculate E naught from delta G naught. And remember that delta G naught is connected to the equilibrium constant K by this equation. Delta G naught is equal to negative RT natural log of K, where R is the ideal gas constant and T is the temperature. And because delta G naught is a part of both of these two equations connect the standard potential E naught to the standard change in free energy, delta G naught, which is then connected to the equilibrium constant K. So let's look at an example of a redox reaction where we know the value for the standard potential E naught, and first we're going to calculate delta G naught, and then from delta G naught we're going to calculate the equilibrium constant K. So here's our redox reaction, and we're going to calculate delta G naught at 25 degrees Celsius from E naught. So for this redox reaction, E naught is equal to positive 1.54 volts, and our goal is to calculate delta G naught at 25 degrees Celsius. In our redox reaction, silver 1+ is being reduced to solid silver, and solid chromium is being oxidized to chromium 3+. Now that we've identified what's being oxidized and what's being reduced, let's write the oxidation and reduction half reactions. So for our reduction half reaction, we have silver 1+ gaining an electron to form solid silver, and for the oxidation half reaction, solid chromium is turning into chromium 3+ and losing 3 electrons. Next, we need to figure out how many electrons are being transferred in our redox reaction. In the reduction half reaction, the silver 1+ cation is gaining an electron, but in the oxidation half reaction, solid chromium is losing 3 electrons, and we need to make the number of electrons equal. Therefore, we need to multiply the first half reaction through by a factor of 3. So now when we add together our reactants, so all the reactants on one side and all the products on the other side, the 3 electrons cancel out and give us our overall redox reaction. Because 3 moles of electrons are being transferred in our redox reaction, N is equal to 3. And since we know that N is equal to 3 and the standard potential is equal to positive 1.54 volts, we're ready to plug into our equation to calculate delta G naught. So I went ahead and rewrote our redox reaction, and our goal is to calculate delta G naught. We already know what N is, we already know what E naught is, and F is Faraday's constant. Here's our equation with everything plugged in. N is equal to 3. There were 3 moles of electrons transferred in our redox reaction per mole of reaction. F is Faraday's constant, which is 96,485 coulombs per mole of electrons, and the standard voltage was equal to 1.54 volts. 1 volt is equal to 1 joule per coulomb, so I went ahead and changed the units from volts to joules per coulomb. Next, we can cancel out some units. So moles of electrons will cancel out, and coulombs will cancel out, and that gives us joules per mole of reaction. And after we do the math, we find that delta G naught at 25 degrees Celsius for this redox reaction is equal to negative 4.46 times 10 to the fifth joules per mole of reaction. We could also write this in terms of kilojoules per mole of reaction. So delta G naught is equal to negative 446 kilojoules per mole of reaction. Notice that a positive voltage and the negative in the equation means that we get a negative sign in the final answer. And when delta G naught is negative, the reaction is thermodynamically favored, which means at 25 degrees Celsius, silver cations will react with solid chromium to form solid silver and chromium 3+ ions. And what this example shows us is whenever the voltage is positive, that means a thermodynamically favored reaction because delta G naught will be negative. Now that we've calculated delta G naught for our reaction, let's calculate the equilibrium constant K at 25 degrees Celsius. So we need to plug in our value for delta G naught, the ideal gas constant, the temperature in Kelvin, and we'll solve for the equilibrium constant. I've gone ahead and plugged everything into our equation, so here's the value for delta G naught in joules per mole of reaction. The ideal gas constant is equal to 8.314 joules per Kelvin mole of reaction, and 25 degrees Celsius, if we add 273 to that, we get 298 Kelvin. Looking at the units, Kelvin cancels out, and so does joules per mole of reaction. And solving for K, the equilibrium constant is approximately equal to 10 to the 78th power. And since K is such an extremely large number, that tells us the reaction essentially goes to completion and all the reactants turn into products. So for a reaction like this, it's not necessary to have equilibrium arrows in here. We can just draw an arrow going to the right. And remember, we started with a positive standard potential for this redox reaction. So to summarize what we've seen with these calculations, a positive value for the standard potential leads to a negative value for delta G naught, so a thermodynamically favored redox reaction. And a negative value for delta G naught leads to an equilibrium constant K that is greater than 1. We've just seen what happens to delta G naught and the equilibrium constant K when the standard potential is positive or greater than 0. Now let's think about a generic redox reaction where the standard potential is negative, so E naught is less than 0. So let's think about the sign for delta G naught if we plug in a negative value for the standard potential. So if we have a negative voltage, the two negative signs in the equation will give us a positive value for delta G naught. A positive value for delta G naught means that the forward reaction of reactants turning into products is a thermodynamically unfavorable reaction. And if we were to plug in a positive value for delta G naught, we would find that the equilibrium constant K would be less than 1. And when K is less than 1, that tells us whenever the reaction reaches equilibrium, there will be a lot more reactants than products. Let's look at a quick summary of what we've learned from these examples. The standard potential E naught and the standard change in free energy delta G naught are related by the equation on the left, and delta G naught and the equilibrium constant K are related by the equation on the right. When E naught is greater than 0, delta G naught is less than 0, and the reaction is thermodynamically favored, which means at equilibrium, there'll be more products than reactants, and the equilibrium constant K will be greater than 1. However, when E naught is less than 0, delta G naught is greater than 0, and the reaction is thermodynamically unfavored, which means at equilibrium, there'll be more reactants than products, and the equilibrium constant K will be less than 1.